So, my name is Jordi. I am a PhD student at CSIC in Valencia, Spain, and I am delivering this talk called Millikelvin Temperature Monitoring for DUNE Detectors on behalf of the DUNE collaboration. So, first of all, I would like to briefly describe what DUNE consists of. It stands for the Deep Underground Neutrino Experiment and is a next generation long baseline neutrino oscillations experiment that is being built in the United States, and it will be a world leader in neutrino physics once it is completed. DUNE science is based on the utilization of the most powerful neutrino or anti-neutrino beam to date, the presence of a very capable near detector close to the neutrino production point, more or less 500 meters away from it, and the underground operation of a massive far detector 1,300 kilometers away from the neutrino production point that will measure the neutrino oscillated flux. DUNE is based principally on the utilization of the liquid argon time projection chamber or LARTPC technology that it will be employed both in the far detector and in some of the detectors in the near detector too. So I will focusing on the far detector complex, which is this complex that is sketched here in the bottom left image. It is an underground facility that is located 1.5 kilometers underground in South Dakota, in Surf, and it consists of four caverns that will be equipped, each of them with a huge cryostat of these dimensions that you can see in this right sketch here. Each of the far detectors will be installed inside. Will have installed inside a liquid argon time projection chamber, and in the first phase of DUNE, we will install two of those modules, and in the second phase, we will install the other two that are corresponding to these two empty caverns in this sketch here. One important caveat here is that we need the liquid argon to be kept extremely pure and stable over time in order to accomplish the DUNE physics goals in terms of precision. So I will try to convince you of the benefits of having a precise temperature monitoring system for these liquid argon time projection chambers. And first of all, I wanted to mention that there is another system in DUNE, in the detector that is called TMS, but in this talk in particular, I will use these letters to describe the temperature monitoring system. So the TMS temperature monitoring system should be regarded first as a risk mitigation strategy, and second also as a potential calibration tool that will be used in combination with computational fluid dynamic or CFD. Um, the current understanding of the liquid argon behavior in such large cryostats is not perfect. So we will use the TMS as a precise slow control of the recirculation system, allowing us for the early detection and the response to potential issues with the liquid argon cryogenic system, or even the detector performance, the liquid argon TPC performance itself. Second, the current CFD models predict a strong correlation between temperature and purity through the liquid argon flow, as you can probably see from this bottom plot here. That is a CFD simulation from one of the two modules, the far detector horizontal drift. On the left image, you see the temperature profile measured at one slice of this cryostat. And as you can see, there is some structure, some temperature structure that is replicated in terms of the shape in the right-hand side image that shows the impurity map. So basically, by resolving this temperature map by means of doing precise temperature measurements, we will be able to predict the electron lifetime or the purity everywhere in the cryostat through CFD simulations. Important is to mention that the expected temperature gradient in these cryostats is of the order of 20 millikelvin. So this sets some requirements on the temperature monitoring system performance. So the principal goal of this system is to continuously monitor the temperature gradients with enough precision to resolve the 20 millikelvin gradients predicted by CFD, by current CFD models in the far detectors. So in order to do that, we set a list of requirements. In this case, I list here five. I separated by them according to the categories that consist of we want our temperature sensors to be relatively calibrated because we're interested in the gradient, not in the absolute temperature, with uncertainties that are below 5 millikelvin. So we will have proper definition of these temperature profiles. Of course, we want some fine granularity over the vertical direction. That is the direction that contains the most useful information according to the currency of the models. But we also want some granularity also along the transversal and longitudinal detector axes. The system has to perform stably and reliably over more than 20 years, which is the DUNE expected operation time, and it has to be passive and minimally invasive with respect to other detector systems of the TPC. So, to pursue that, we have developed an intense R&D based on two technologies. The first one is the utilization of the RTDs, that stand for resistance temperature detectors. What we have used are these PT100 series from Lakeshore that are ideal for high performance cryogenic applications. You can find more information about this series in this link here. They look like this in the top image, the top right image here in the slide. And we read out them using the 4-terminal configuration, ensuring that we only measure the RTD resistance as we measure at the very end of the terminal of the platinum sensor. We have all of them connected in series, and we cite them with the same 1 milliampere current. So in this way, we make the gradient measurements to be totally independent of potential current source fluctuations. We have a calibration strategy, calibration procedures, ATIFIC, that have allowed us to relatively calibrate a large number of RTDs enough to instrument the whole cryostat with a precision better than 5 millikelvin. The calibration setup that we have employed consists of this polystyrene box that has a hole in the center where we host the liquid nitrogen that we employ to calibrate those RTDs. It consists of a series of several concentric volumes where we place our RTDs in the innermost volume, following this sequence here. The argon that is in the, let's say, in the outer volume serves as insulation for the innermost volume, and that generates a very stable atmosphere or environment in the innermost volume that allows us to have the same temperature on all of them and to be able to calibrate the sensors in this innermost volume. We use this current source here described in this paper, and all of this setup is also described in the paper, so you can have a look at it if you are interested in that. So here are some more insights of how this looks like. We divide our sensors in sets of 12 sensors, and we subject them to 4 consecutive thermal baths from room temperature to liquid nitrogen temperature. And you can see here a look of how the readout of the temperature measurements when the sensors are immersed during these 4 consecutive baths look like, and we evaluate the calibration constant as the average of the means of each of these 4 consecutive runs, and the uncertainty we associate to the standard deviation of these 4 means. You can see how the 4 measurements that talk about the repeatability of the calibration constant are distributed between 2 millikelvin, more or less. We created a calibration structure that we proved also in this paper that allows us to calibrate a large number of sensors. We proved it with a set of 48 sensors, and what we do is to create sets of 12 sensors, and from each of the sets we raise 3 of them and we calibrate them all together. So we have sensors from each of the 4 sets here, and this allows us to calculate the calibration constant between any pair of these first round sets by just computing the appropriate offsets with respect to the sensors that are present in both sets. So this was the first line of research, of R&D in ATIFIC based on RTDs, and we have a second line which is based on FBGs or fiber Bragg gratings. This technology has been widely used in industry, but it will represent the first time that this technique or this technology is used in a liquid argon type projection chamber for a high energy precision, high energy physics experiment. So basically, these FBGs are modulations of the effective refractive index of of the fiber core at specific physical locations that create a grating. You can see a sketch describing this sensor here in the bottom left image, so that when we send some light through the fiber, just a very narrow portion of it of the spectra of the light that we send through the fiber get reflected at each sensor, at each grating, and it produces a back peak that gets reflected back in the fiber, and we measure it via a spectrometer. The position of this black peak depends on the temperature of the fiber, on the humidity, and on the strain. So any change on any of these quantities translates into a shift on your black peak position. So by tracking this black peak, you are able to determine the cause that has caused the shift. So the R&D at IFIC has consisted into obtaining a system with enhanced temperature sensitivity of these FBG sensors, and to keep the strain on the fibers under control in order to do a temperature, let's say, a strain-free temperature measurement. First of all, you have to know that the temperature sensitivity of these sensors is very limited at liquid argon temperature. So we have done a vast majority of the R&D has consisted into enhancing this temperature sensitivity, that we are able to measure it with this pressure setup. That is a pressurized vessel that is filled with liquid nitrogen and allows us to control the temperature within a wide range of cryogenic temperature from 77 to 92 Kelvin by means of pressure control. And it allows us to measure the FBG sensitivities within this range. That includes the liquid argon temperature, which is 87 Kelvin. Then we have this other setup that is the 1.5 meter dewar. It is a handmade 1.5 meter tall dewar that is aimed to replicate the detector-like conditions that we will find in the fire detector modules. It creates a very stable cryogenic environment with a replication of the, let's say, liquid argon or liquid nitrogen column in this case, and it allows us to study the small temperature variations and the stability of the readout. So some plots about the performance of these FBG sensors at cryogenic temperatures. The enhancement of the temperature sensitivities of these sensors comes from the combination of the proper inscription of the FBG sensors on the fiber cores, the own properties of the fiber cores, and more important, the fiber coating. Okay, we have tested several coatings. We have worked with several manufacturers to coat our fibers with different materials, and we have developed a peak coated sample that offers 19 picometers per Kelvin sensitivity in the range of temperatures of interest. And this implies a temperature gradient resolution using this technology of the order of 2 millikelvin, considering the current interrogation technique that allows us to track the peak position with a resolution of something like 30 femtometers. So in these plots, I show you how we do that. We are able to change the temperature, as you can see in this left blue axis here, from 76 to 90 Kelvin. By that is measured through one of those RTDs, and in red is the signal, the peak position as measured by one of the sensors on these fibers. And as you can see, they follow the exact basically the exact same profile. So by taking the values of the temperature and wavelength at each of the plateaus, we're able to create these lines that allows us to extract the temperature sensitivities of the different samples, and the peak one is the green one here with 19 picometers per Kelvin slope. So how do these technologies, let's say, are implemented in the fire detectors? So the RTDs will be used in both detectors, and in the horizontal drift we will only have RTDs. So the horizontal drift, the fire detector horizontal drift consists of an RTPC that has 3 anode planes and 2 cathode planes. On the anode planes, we will install 600 RTDs on them. Then we will also use temperature sensors to monitor the temperature of the liquid argon that is being thrown in, the pure liquid argon that is being thrown in by the internal cryogenic lines. We will install 16 sensors on them. Then there are 4 purity monitors at each of the 4 corners of the cryostat that will measure the electron lifetime in situ, and we will install also some temperature sensors on them. And also we will have some sensors on the OLED measuring the gas profile above the liquid interface. So we have prototyped this in the ProtoDUNE horizontal drift prototype at CERN, which is the prototype of the farthest horizontal drift. And here is a view of the interior of that cryostat. So this represents all the, let's say, temperature subsystems that we have installed and operated there. I want to highlight the Valencia T-gradient subsystem, which is an array of 48 RTDs located in one of the corners of the cryostat. And on the opposite corner, we have the Hawaii T-gradient, that is an array of 24 RTDs that also measure the whole vertical profile. We also have sensors on the APAs, on the purity monitors that are also measuring the electron lifetime in that cryostat, on the pipes, and in the ULAGE too. Also, we'll have some of them measuring the temperature close to the liquid argon recirculation pumps that suck let's say, the dirty argon from the cryostat. This is a plot that I like to show when showing the performance of the system. So because it shows that as predicted by many CFD simulations or by the CFD simulations, the temperature map is very homogeneous overall the cryostat, showing some difference at the top that I now will explain. So in blue, what you see is the temperature profile measured by the Valencia T-gradient in one corner of the cryostat, and in orange, the one measured by the Hawaii profiler in the other corner, and the green one is the one measured by the purity monitors that is next or close to the Hawaii. The difference here at the top comes from the fact that the Valencia T-gradient is close to the liquid argon inlet pipes that throw in warmer liquid argon. So we are able to detect this difference in temperature because of this proximity to the liquid argon pipes. So the current status of the CFD simulations is that we have a model that we are still tuning in order to not only capture the large scale structures but also local details. Current CFD models fit reasonably well to data, and we are properly capturing local features like this 1 meter temperature bump induced by the proximity of the Hawaii profiler to the bottom APAs, cold electronics that deliver a lot of power into the argon. And as I said, the model has not still converged for all cryostat or the detector operation conditions, so we are still working on it. Then we have the other technology, which is the fiber-based temperature monitoring system that will consist on the deployment of several fibers crossing the 3 detector planes that will make up the far detector vertical drift, that will have 2 anode planes and 1 cathode at the center. So in this top layout here, what you are seeing is the layout of the position of these fibers in the cryostat, and considering all the fibers that we will install in that cryostat, we will have more than 1,300 sensors, FBG sensors, measuring the temperature through this novel technology. We'll also have sensors on the inlet pipes, on the purity monitors, and in the ULAGE, but we will be using RTDs in this case, as we do in the horizontal drift. We have prototyped this design at CERN in the ProtoDUNE vertical drift, and we installed it last year, and is still now taking data as the cryostat is full. And we have been able to monitor the cooling down of the cryostat by means of looking at this FBG data, and we have been able to evaluate the performance of the samples in situ. You can see here some images about the instrumentation of that system. So this leads me to the summary and conclusions, and we have designed a high precision temperature system for both far detectors that will allow us to monitor the health of the cryostat and to perform a relative energy scale calibration. And we have validated both technologies, both in the 2 far detector prototypes at CERN, and we are working in the conversion in the CFD simulations in order to make them converge with the data that we took in in the prototypes. So thanks for your time.